let's try this. Let's see what this thing is actually telling us what to do. Okay. So, the first thing about this, it says, okay, Kruskal's algorithm, let's input G, which is a connected weighted graph within vertices, and step 1 and step 2 is just initialize the set T and initialize the set E, which is vertices. So this is what we're going to begin with. The input. This is the graph G that we are going to begin with. All right. Now it says, well, okay, so we're just inputting this graph, and what we're going to try to do with this graph, this weighted graph, is find the minimum spanning tree of it. Okay. So let's start off with the very first statement. Now, while n is less than or equal to n minus 1. Now, all right, in some books this will actually say less than. That begins if you depend at n which equals 1, where n which equals 0. Okay? And you don't want to go over it because n is the number of vertices. Okay, so let's just start with the connection. And so the first connection that we're going to ask is find an edge E of E out of that set of least weight. So what is this? The edge of least weight? That would be 1, right there. Okay. So if I consider this, I'll say, well, great. Of A to B that's that, n which equals 1. Well, let's go ahead and define what n is also. All right, so we can start off with n which equals 1. And how many vertices do I have? I have 1, 2, 3, 4, 5, 6, 7. N is going to equal 7. Okay? Okay. So this is our first step. We find an edge of least weight. All right. Now delete E from the set of E. Okay? Well, that means that E would equal 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so I can't use that educate. Yeah? Okay. Right. Now it says if addition of E to the edge set of T does not produce a circuit, then add E to the edge set of T. So if I was talking about T in the general sense of endpoints, now you would store that as an array. Saying edge 1 is going to connect endpoints A and B. Okay? And that says if it does not produce a circuit, then add to the next step. Okay? So, now we have to consider M, which equals 2. Okay, so we have our first connection, which is A and which is B. And now we're going to go to M, which equals 2. All right, now we have to find the edge of least weight of this next set, okay? And so for n which equals 2, we look through our graph, and what is the next one of least weight? That's going to be 2, right there. So, n which equals 2 is going to be A connecting to B, which has a length of 1, and E connecting to F, which has a length of 2. Okay, so we found the least weight of E, okay? So the problem says find an edge E within E of least weight. Now what is left over from the previous problem is 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so all right, well the next one would be 2, as long as it doesn't follow a circuit. Okay? And delete E from E. Great, that means that E would equal 3, 4, 5, 6, 8, 9, 10. Okay, so we deleted that one. Okay? And if addition of E to the set of T does not produce a circuit, then add E to the edge set of T. Alright. So that would mean that T, we have edge and endpoint function So 1 would be connected to A and B, and 2 would be connected to E and F. Okay. And remember that n is 7, so we're going to have to go up to 6. All right. So this is a while loop while m is less than or equal to n minus 1. So while m is less than or equal to 6. Okay. Now, the next one says m which equals 3. Okay? All right. Now we're going up to m which equals 3. So we're going to have the ones we had before. A connected to B, which is upon 1. E connected to F, which is connected by 2. And E, which is connected to D, which is connected by 3. Okay, so we found the next lowest one. And so this would change E into set 4, 5, 6, 7, 8, 9, well, I'm running out of room, but 10. Okay. And T's edge to endpoint so that would be 1 is connected to A and B. 2 has to be connected to E and F. And 3 has connected between E and D. Okay. Now all of this at this point is pretty straightforward because we just went from a weight of 1 to a weight of 2 to a weight of 3 in describing these connections. But then on the next step is where you start getting into, well, is this concept really giving you a minimum spanning set. And so, this, we got a couple people right now. I'll wait just a second. The question about the next step of this problem is about 3C. Okay? And 3C of the algorithm says, if addition of E to the edge set of T does not produce a circuit, then add E to the edge set of T. So there is a condition upon adding an edge to the set. So, remember that when we were talking about what is a circuit is a closed walk. My memory serves, that does not repeat edges. So, a closed circuit, we're going to have to go to, all right, so the next question becomes, okay, so we found our first three, okay? And then the next one would be, find an edge E of least weight that is corresponding with the set. Sorry, it's the next problem that does that. What is the next corresponding weight? Is actually going to be 4. Where we're going to run into an issue in this problem is if I try to add edge 5. Okay? So now what would happen if I added edge 5 to this? It would create a closed circuit from E to F to D and back to E. So edge 5 cannot be included because that would create an actual circuit. We can't add 4 though. Sorry, got a little ahead of myself. Okay. So, n which equals 4, A, B, y'all are fine. F, E, D, y'all are fine. And then C, this would be 1, 2, 3, and 4. And E would become 5, 6, 7, 8, 9, 10. And T, with our edge to endpoint function, okay, that would be 1, 2, 3, and 4. That would be AB, F, D, and then what would our last one be? Would be DC. Okay, so that's the 4th iteration of the algorithm. Okay. Now to consider the 6th iteration, or the 5th iteration of the algorithm, what we're going to have to do is we're going to have to find an edge E inside of here. Okay. So we've already gone through 1, 2, 3, and 4. I can't include 5. That would create a circuit. Okay? Because I can't include that guy, what is the next number that is the biggest number that is not going to create a closed circuit, a closed walk? It's going to be 6. We just have one more after this one. Okay. So, for m which equals 5, we would have A is connected to B, that connection, and then where was that? That was G. G is going to be connected to F. That's 1, that's 6. F will be connected to E, and that's got a 2 right there. Then E will be connected to D, and that had a 3 right there. And then C, which was up here, has to be connected to D, which is 4. Okay. And so what are we down to at this point? Capital E would be 5, 7, 8, 9, 10. Okay? And whenever y'all are coding in MATLAB, this 5, 7, 8, 9, 10 that I'm writing over on this side of the problem, it shows up as an array on the right-hand side of the screen, so you can actually just click on these little boxes and it'll show you how many numbers are in there. And then you'll have another array, which is going to be your edge to endpoint function, which will be t. And if we say edge to endpoint, create another array. Go 1, 2, 3, 4, and 6, which would be AB. I know y'all are writing a lot of this stuff over again, but there's a point to this. EF, ED, BC, and what was the last one? FG. So we've already eliminated 1, 2, 3, 4, and 6 from the set of E, which is the edges that we could possibly use. All right, and now we're running through the while loop again, and it says while m is going to be less than or equal to n minus 1. All right, well, n was 7. That's the total number of edge points. And m is going to equal 5. So we just need one more step. So we have to look back at our original graph and say, okay, I've deleted 5, 7, 8, 9, 10 from this. I only have 5, 7, 8, 9, 10. I've already deleted 1, 2, 3, 4, and 6. And then I have to ask myself, what is the next least weight? Well, if I've already deleted 1, 2, 3, 4, I can't use 5. I picked up 6. If I used, the first question is the least weight. What is the least weight? The least weight would be 7, because we only have, we can't use 5, and we have 7, 8, 9, and 10. So the next one that will not create a closed loop in the circuit or a closed walk would be 7, and so then we go down to m, which equals 6. Okay, now m, which equals 6, would pick up A connected with B, which had a length of 1. We have G connected with F, the length of 6, E connected with F, which had a length of 2, D connected with E, which had a length of 3, C connected with D, which had a length of 4, and B connected to C, which had a length of 7. Okay? And so our set E upon that point would not include, what's not included is in our minimal spanning tree, which would be 5, 8, 9, and 10. Okay. And so we talk about T's edge to endpoint function. Yep. 1 would connect A and B. 2 would connect E and F. And then 3 would connect E and D. 4 would connect D and C. 6 would connect F and G. And I'm almost off the screen, but, well, I'm not out of paper. 7 would connect B and C. Okay. And so on the homework with a general minimum spanning tree, what it's going to ask for is this set on the right-hand side of this one. That's going to be the set of connections. That's your edge to endpoint function. So it's going to actually, it's not going to ask you for which length of the edges it is. And actually the length is identified in this case, but they're really going to ask for what the endpoint connections are. And so that gives you a minimal spanning tree for a graph